let's take a look at work. Work in physics can be defined in a few different ways. One way is that work is a transfer of energy. This is a nice definition because it's short and sweet, and also because it refers to this idea of energy, which we've been talking about. So, transfer of energy, that means that it's the energy either added or removed from an object. Okay. Another way we could define work is that it's the product of the force on an object and the component of the displacement of the object parallel to that force. That's a little tougher to maybe understand right away, but before you think about it too much, let's add another definition. Let's say that work can also be defined as the product of the displacement of an object and the component of the force on the object, which is parallel to the displacement. Now, those two definitions are a little tough to understand right away. They're a little mathy, and it turns out that the reason why they're mathy is because they're based on something in math called a scalar product or a dot product, which you may have encountered. And we're going to take those two definitions and kind of put them to the side, but they are useful. Notice that those two definitions relate work to the idea of force and displacement, which are things that we've seen before. So they kind of connect work to previous ideas. But let's put those to the side. The symbol for work in physics is often a capital W. The unit of work is the same as the unit of energy. Work is a transfer of energy. It's energy moving back and forth. So same unit as energy, joule. And also work is a scalar quantity. Work does not have direction. It only has magnitude. Now let's take a look at a couple introductory examples about work. Let's say that you have a block, and that block has 5 joules of energy to begin with. Then you come along, and you do 3 joules of work on the block. How much energy does the block have at the end, after you do the work? Well, let's see. The block started out with 5 joules of energy. I don't know what kind of energy, but that doesn't really matter. All it is 5 joules of energy. Then you transfer 3 joules of energy to the block, right? If you did 3 joules of work, work is a transfer of energy. That means that you transferred 3 joules of energy to the block. Well, if your block started out with 5 joules of energy, and then you transferred 3 joules to the block, in the end, you ended up with 8 joules of energy in the block. Let's look at a different example. Let's say that you have a block with 10 joules of kinetic energy and 0 joules of potential energy. And you come along and you do negative 6 joules of work on the block. How much energy does the block have in the end? Well, let's see. What does that negative 6 joules of work mean? What does that negative sign mean? Well, it doesn't mean direction, because work is a scalar quantity. It is not a vector. It doesn't have direction. So that negative sign does not mean left or down or anything like that. What it does mean is that it's energy being transferred away from the object. That negative sign, again, means that energy is being transferred away from the object. So, if you do negative 6 joules of work on something, you're transferring 6 joules away from the object. You're taking 6 joules of energy from it. So, you started out with 10 joules of energy. You removed 6 joules of energy from it. So you end up with a block that has 4 joules of energy. And if we assume that in the end it has kinetic energy, and that the 4 joules of energy is kinetic energy at the end, then this can kind of make sense. We can start to build some intuition for this. The block started out with 10 joules of kinetic energy. And remember, kinetic energy is related to motion, so that's 10 joules of motion energy. Then we removed some of that motion energy from it. So it ends up with less motion energy. The box slows down in this situation. If you remove kinetic energy from it, you remove motion energy from it, which means that it will not be moving as much. It will slow down. So throughout all of this, we haven't talked about how you would do work, how you would transfer energy. Well, in order to transfer energy, there has to be some kind of interaction. If I'm going to add or remove energy from a block, or a person, or a planet, then there has to be some kind of interaction. And interactions in physics are related to forces. So somehow force should be involved with work, with transfer of energy. And I'm going to write down an equation. Work is equal to Fs cosine theta. The W represents the work done on an object by a force. The F represents the magnitude of the force acting on an object. The S represents the magnitude of the displacement of the object. And the theta in this equation is the angle between the force and the displacement. Now, toward the beginning of this, I mentioned those two definitions of work, which were a little mathy and not necessarily the clearest definitions. This is a mathematical representation of those two definitions. And we're not going to dive too deep into that connection, but I will say that this is related to something called a dot product or a scalar product, which you may have seen in math before. If you haven't, that's all right. But I will write down how work is defined as a dot product or a scalar product, but we're just going to leave it at that. Now, let's use this equation. Let's apply it. Let's say that we have a situation where we have a crate sitting on the floor, and then you come along and you apply a tension force to this crate. And as you apply a tension force at this angle, the crate goes through a displacement across the floor. And I want to know, through this interaction, how much work have you done on the crate? How much energy have you transferred to the crate? Well, let's put some numbers in here. Let's say that this angle is 30 degrees. Let's say that the displacement is 2 meters. And let's say that you've applied a tension force of 50 newtons here. Well, the work that you do on the crate is equal to Fs cosine theta. Well, in this situation, you've applied 50 newtons of force. And the F that goes in here, remember, is the magnitude of the force. It's the amount of force without any information about the direction. So the F is 50 newtons. The displacement of the object is 2 newtons. And again, we put in the magnitude of the displacement without any information about its direction. Okay, so we got 2 meters for the displacement. And then theta in this equation is the angle between the force and the displacement. And in this situation, the angle between the force and the displacement is 30 degrees. So we have 50 newtons times 2 meters times the cosine of 30 degrees, 86.6 joules. That is the work that's been done on this crate by that force over this displacement. Okay. Let's look at a different example. Let's say that you apply the same 50 newtons to the box as it moves 2 meters, just like it did before, but now the force is applied in this direction. The force is being applied parallel to the displacement. So let's see what changes here. Well, work is equal to Fs cosine theta. Well, the force being applied is 50 newtons. The displacement is 2 meters. Again, take away all information about the direction. And then the cosine of theta. Theta is the angle between the force and the displacement. Well, the force and the displacement are in the same direction. So the angle between them is 0 degrees. So we have 50 newtons times 2 meters times the cosine of 0 degrees, which is 100 joules. You transferred 100 joules of energy to the crate. And notice, in this situation, you apply the same amount of force over the same displacement. It's just that you apply it in a different direction. In this situation, you ended up doing more work on the box, on the crate. Let's look at a third example. Let's say that the box moves to the right 2 meters. You apply a force of 50 newtons, but now you're going to apply the force of 50 newtons to the left. So work is equal to Fs cosine theta. Okay, well, force is 50 newtons. Remember, no direction information goes into here. The displacement is 2 meters. And the angle, well, the angle between the force and the displacement here, well, your force is to the left, your displacement is to the right. The angle between those two things is 180 degrees. So it's cosine of 180 degrees. So you end up with a work of negative 100 joules. In other words, you transferred 100 joules of energy away from the crate. You took 100 joules of energy away from the crate. So compare the second to the third example. In the second example, you're adding energy to the block. You're providing energy to the block because the force and the displacement are in the same direction. In this third example, you're removing energy from the crate. You're taking energy out of the crate because the force and the displacement are in opposite directions. Last example we'll look at. Let's say that the box moves to the right 2 meters and you apply a force upward that's equal to 50 newtons. How much work are you doing in this situation? Well, in this situation, the block is moving to the right, you're applying a force upward, so you're really not having an effect on its motion to the right, at least not a direct effect. You're not helping it move that direction, you're not harming it. But in this situation, that force is perpendicular to the displacement. So when we solve for the work is equal to 50 newtons times 2 meters times the cosine of 90 degrees. 90 degrees is the angle between the force and the displacement. So in this situation, well, the cosine of 90 degrees is 0, so the work done by that force is 0 joules. No work is done by that force. That force didn't add or remove any energy from that block.